So we spent a lot of time on the mass balance. Now we need to move into an energy conservation statement. Bernoulli's equation. Last time I think we derived it, didn't we? From an energy perspective. And what did we say? We said that you could write an equation that has a number of assumptions. Here are the assumptions. So along a streamline, same chunk of fluid, flowing at steady state through our system. It's incompressible. Yes, there's a compressible version of it, but let's just deal with the incompressible version of Bernoulli's. There's no frictional effects, no inviscid, hence there's no viscous dissipation of mechanical energy, which would make it get warmer unless there was heat transfer out of it, but it would be making things warm. Friction does that with mechanical energy, turns it into internal energy. No heat transfer, no work transfer. And we're left with this nice equation. This is the favorite form, or one of the more favorite forms, because every term has units of pressure in it. So P plus 1/2 rho V squared plus rho GZ is equal to a constant anywhere and along that streamline. The Bernoulli equation, it's a statement of the conservation of mechanical energy. Pressure is energy? In a way it is. All you have to do is multiply the pressure, like in kilopascal, times meter over meter, and then you get kilojoule per meter cubed. It can be interpreted, especially in Bernoulli's equation, as energy per unit volume. And this sometimes comes in very handy if you can recall it and use it. Energy per unit volume. If I take that equation and I divide everything by rho, I get a second equation. The second equation looks like this. You say, all I did was divide by rho. You're absolutely right. That's all you did, but did you get any insight in there? Sure, because we look at each of those terms, and we look especially at this term, and we're reminded, it's maybe not as clear as P was pressure, but this term is V squared over 2. It's specific kinetic energy. Coming out of thermo, specific kinetic energy, meaning kinetic energy per unit mass, or a form of energy per unit mass. We call that sometimes head. Loosely we'll call that head. But really this is probably the clearest form of Bernoulli's equation as an energy statement. It's the energy per unit mass. Each one of these terms, 3 terms, the pressure over rho sure doesn't look like energy per unit mass, but it can be interpreted that way. This term sure doesn't look like it, but it is. That one may be a little clearer. That's like potential energy per unit mass, gravitational energy per unit mass. This one's kinetic energy per unit mass. The sum of the 3 components is equal to a constant along a streamline. What did we do to get to the last form of the Bernoulli equation? Right, so either go back to the first one, divide by rho G, or the second one and divide by G. What do we have here? We have, it's more clearly seen, but if you look at this term right here, the last term, that has units of elevation. That's called head. All right? So Z, just meters. And you think meters, that everything in this whole equation has units of meter, 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 but how can you interpret that as energy? That's challenging, probably more challenging than pressure is energy, but it's energy per unit weight. Weight of what? Weight of the fluid packet that's flowing through the system. This one is head. This is commonly called head. Head has units of length, as if a long manometer. Okay? Often they sketch as long manometer, give you an idea that that head can be measured by a fluid column in a long manometer. It's energy per unit weight, and there's the units and how you make it look like something joule per Newton or kilojoule per kilonewton. Just like this one was kilojoule per kilogram, kilojoule per meter cubed. Let's talk about that siphoning that we just demonstrated. So we have a tank, and that tank has some fluid in it. It's filled to that level. And we introduce a tube, and I'm going to show the tube being submerged. There's the end of the tube. It goes up, then it comes back down. into another tank where I'm even going to show the fluid level down here. But the tube ends right here. All right, so that's our tube to use for siphoning. And what I want to do is I want to talk about the flow that comes out. The fluid will come out here, out of that tube. And what we want to do is apply Bernoulli's equation to understand and predict the speed at which it comes out. The speed down here that comes out of the tube. Well, to apply Bernoulli's equation, we want to go along a streamline. Let's start the streamline at the top, just like we did last time we met, okay, at the top of the tank. The streamline goes into the tube, along the tube, inside the interior of the tube, all the way to right there. So that's our streamline. And we want to introduce states along that tube. Indulge me, I'm going to call this state 1. I'm going to also, for discussion purposes, call point 2, location 2, is just inside the tube that's submerged. It's just inside the beginning of that tube. Okay? I'm going to talk about state 3 in a minute, and it's the location of the highest elevation of the tube. Then I'm going to talk about a state 4, which is exactly the same elevation as state 2, but it's now not on the upside, it's on the downside of that tube. So state 2 and state 4 have the same elevation, but 2 is not outside the tube, it's inside the tube. 2 is just inside the tube a little bit. And then state 5, the very last, will be right at the exit of the tube, state 5. Okay? So somebody said, I want you to predict the exit speed, V, this speed right here, of that flow coming out of that siphoning tube. How would you use Bernoulli's equation to do it, assuming steady flow? In VSIT, we're neglecting frictional effects. Okay? It's incompressible, something like a liquid water. How would you do it? Use Bernoulli's equation from point 1 to, let's say, 5. So can you write Bernoulli's equation from point 1 to 5? So it's okay. At point 1, I talk about the pressure at 1, the speed at 1, squared, the kinetic energy, the elevation at 1, and that has to equal to the pressure at 5, the kinetic energy at 5, and the elevation. See how we do that? So we write the both right side and left side, the beginning point, the ending point of my streamline. So one point's 1, the other point's numbered 5. And we interrogate, what about the pressure at state 1? It's atmospheric pressure. How about the pressure at state 5? Atmospheric, can they cancel? And if you wanted to, just like when we did fluid statics, you would say, hey, I'm going to just work in gauge pressure. And both of those would be 0 gauge pressure, true? All right. How about the speed and the kinetic energy at 1 half rho v1 squared? Is negligible, 0, because this diameter is so large compared to the tube diameter. Now, in the demonstration we just had, the water bottle's diameter wasn't 10, 20 times larger than the tube diameter, and you could see that water level fall. Okay, if you wanted to, you could account for that, but have a large tank. Okay. Z1 is higher. We don't have a coordinate system. You could introduce a coordinate system. You could put it down here if you wanted to, and you could go up. Z is going up from the bottom of the bottom tank. Some coordinate system. How about 1/2 rho V5? That's what I want to solve for. I want to find V5. I don't know that. I hope I get an equation out of this that will let me calculate V5. And rho g z5. So what we do is we rearrange these terms, and you find that the v5 with a little algebra is equal to g 2g z1 minus z5 square root. So it depends on the height difference here. We could call that h. We could replace this by h. Let me ask this a question. Let's say I actually made some measurements here. Would I expect V5 actual to be greater than the square root of 2gh, equal to or less than square root of 2gh? The real one that I'm actually physically measured. Less. Why? Bernoulli's throws out viscosity. It neglects frictional effects. Friction's going to slow down the flow. So the actual will be less because of the frictional effects. Now let me ask you this question. We predicted the speed that it exits at 5. I'm going to pause after I ask this question. I'm going to go around. I want you to tell me the relationship between the speed at 5 and the speed at 4. Is the speed at 4, what do you mean the speed at 4? The downcoming speed in the tube at location 4, which is at a higher elevation, is it greater than the speed at 5, equal to the speed, don't call it out, or less than the speed at 5? You have to work that out. I pause and I walk around and get your answer. All right, so we made the observation that the diameter of the tube at 5 is equal to the diameter of the tube at 4 is equal to the diameter of the tube at 3 is equal to the diameter of the tube at 2, right? The diameter doesn't change. The cross-sectional area of the tube is the same at all of these. True? And we also know that our fluid is incompressible. Incompressible. Did the density of the water at 5, is that the same as the density of the water that flowing through point 4? Is that the same as the density of the water? And we also said you have conservation of energy, Bernoulli's equation, but sometimes you pull out and use in the analysis the conservation of mass. All right? Is the mass flow rate in the tube coming out at 5 equal to the mass flow rate in the tube passing through point 4 the same as the mass flow rate passing through point 3? You wrote that. So you wrote that. You wrote it just like that. That's the perfect way to write it. That explains. So if the mass flow rate's the same, m dot 4 is equal to m dot 5. You expand the mass flow rate for flow in a tube going across the cross-sectional area of A, rho A4 V4 equal to rho A5 V5, true? The densities, areas, what about the speeds? They're the same, they're equal, they're equal. Most of you were trying to say that one was higher than the other. Why? You're thinking energy still, right? Okay. But
so the H doesn't affect.
That's right. As long as the cross-sectional area is not changing, and as long as the density is not changing, then you're stuck with, hey, the speed is the same through the tube. Even at the top, is the velocity at 3 equal to that? How about the velocity at 2? It is. It's always the same no matter where you're at. I'm going to ask you this question. The pressure at 4 versus the pressure at 5, is it greater, equal, less? And once you answer that question, you can say the same thing. Pressure at 3 versus the pressure at 4. Greater, equal, less. And then Pressure at 3 compared to pressure at 5. Don't worry about it. I should ask one question at a time, not a bunch of questions. All right, so what was the class consensus? P4, what is it? It's less than, right? Okay, how much less? What's the equation? How do I get that equation? Somebody back there had it. How'd you get it? Yeah, but you're too far ahead. All you need to do is step back and say, I used the principle of the fundamental theorem of calculus. Or I used L'Hopital's rule. We used the Bernoulli equation. That's music to my ears. You applied the Bernoulli equation between state 4 and state 5. The Bernoulli equation applies any 2 points along the streamline. They don't have to be the endpoints. Often we put them the endpoints, but they can be intermediate points as well, true? So if you apply Bernoulli 4 to 5, just write it out the first time. So Bernoulli 4 to 5, what does it look like? Then what you were saying is, now I notice that this speed right here is equal to that speed right there. Hence, their kinetic energies, the velocity pressures are the same. They cancel on both sides of the equation. And we want to know the relationship between P4 and P5. And so P4 is equal to P5 plus rho g Z5 minus Z4. Well, Z5 is less than Z4, so maybe I want to write it minus rho g Z4 minus Z5. So P4 is less than P5 by rho g, this elevation difference. It's almost as if it was just fluid statics. Wouldn't that be the same if it was just fluid statics? No flow in the tube? That's interesting. Now, can you tell me about P3? It's at the highest point. It's at the lowest pressure in this whole system, isn't it? And you can find that by Bernoulli's equation. Let me ask this question. Somebody gets a little drill, and they come out and they go, bzzz, they drill a hole right in that tube, right at point 3. Then they pull the drill out. Is air going to rush into the siphon tube at 3? Or is water going to squirt out at 3? I'm going to pause and let you, you have to answer that question. All right, to help guide us, what is the gauge pressure at 5? Somebody says 0 psig. Is that person right? What is the pressure at the outlet 5? 0. It's 0 pressure gauge. Now, if I look at pressure at 4, and I put a gauge pressure right there at 4, will it show a positive gauge pressure or a negative gauge pressure? What will it show? What does that mean about the pressure in the tube at 4? It's less than atmosphere. Is it really in a state of vacuum? Yeah, it's in a state of vacuum. Its pressure is less. And the vacuum gets stronger as you go up higher. We get up to 3. That's the highest point. This is the strongest vacuum. That pressure at 3 is going to be negative rho g Z3 minus Z5 gauge. If I pop a hole in the tube there, the air will rush in because the pressure at 3 is less than the atmospheric pressure. It will break the siphon. The siphon will be broken. You won't be able, it won't work anymore. What about the pressure at 2? I want to compare the pressure at 2 to the pressure at 3. Higher or lower? It's higher. The pressure at 2 is higher. But it's still in a state of vacuum. How about the pressure at 2 versus the pressure at 4? They're equal. And we said 4 was in a vacuum. So this is very, very interesting. This is a stationary water tank. I come over here to the side, very far away from the tube. I come down, I look at the pressure at this elevation in the tank, over here to the side, far away from the tube. What's the pressure there? Rho GH. Is it in a state of vacuum? No, it's a hydrostatic head. There's a heavy water on top of it, right? It's got positive gauge pressure. But inside the tube, right there, at state 2, what happened? It's a vacuum. And that's really what's drawing the water into the tube. It's drawing the water into the tube. I didn't say this was easy. I thought maybe it was insightful, but I didn't say it was easy. And if you get the siphon down, maybe you're a long way to applying Bernoulli's to a lot of other problems. If I wanted to get the volumetric flow rate that was flowing through here, or the mass flow rate is the mass density times the speed times the area, true? How would I get it to drain that tank faster? I would increase the diameter of the tube. I would also try to increase the speed in the tube. How can I get the speed in the tube to get higher? Change the elevation difference. The elevation difference, right? Right? Okay, let me ask this question. Should I, if I took the tube and location 2 is, let's say it's 3/4 down deep into the tank. The tube is 3/4 down, submerged, all down, okay? I say don't submerge it so far. Submerge it only 1/5 of the way. Put the end of the tube, state 2, right there. Will I have increased the flow in the tube? I pause, I let you answer that question, I come around and look at it. Okay, so notice that this equation here is Z1 minus Z5. Was it Z2 minus Z5 or Z1 minus Z5? And so it doesn't matter if Z2 is a little higher or if Z2 is a little lower, as long as you got it in the water. Nozzle. Put it horizontal, bring it to reduce the cross-sectional area. Put a streamline straight through the nozzle. We have inlet area 1, very large, but not infinite, to the area 2, which is in the throat at 2. And we apply Bernoulli's equation. What about the elevation difference between 1 and 2? We put it horizontal. Even if you turn the nozzle up or down on the side, the nozzles are so small in length that it's negligible elevation difference. It's not like a pipe where it's, could have a significant elevation difference. Now, what about this and this one? These are my velocity pressure at 1. This is my velocity pressure at 2. Which one's larger? 2 is larger because it's going faster. Okay. If the sum of the static pressure, P2, plus the velocity pressure at 2 is equal to the static pressure at 1 plus the velocity pressure at 1, that's true. True? They're true. I can come up here, I put a little pressure gauge, I measure static. I put a little pressure gauge right here. I measure the static pressure at 2. Is P2 lower than P1? Yeah, it is. And so the throat has a low pressure. We can write that P1 minus P2 is equal to PVEL2 minus PVEL1. That's all Bernoulli, that's all energy. Can I also do mass or continuity? What does the mass or continuity equation say about this? Does it say that the mass flow rate at 1 is equal to the mass flow rate at 2? Does it say rho A1 V1 is equal to rho A2 V2? Yes, yes. So we cancel the rows. And now we have a relationship between the velocity at whatever, do you want to remove one or the other? Velocity at 2 is equal to the velocity at 1 times A1 over A2. Is that true? We could bring that in over here. We have 1/2 rho V2 squared minus V1 squared. That's 1/2 rho, let me do this, V1 squared times A1 over A2 squared minus 1. So we can read this. This tells us how much that pressure difference will be. P1 is higher than P2. There'll be a reduction in pressure equal to the velocity pressure at 1, 1/2 rho V1 squared, times this term, A1 over A2 squared minus 1. Let me do this. If I said that the area is equal to pi d squared over 4, could I put it as 1/2 rho V1 squared diameter 1 to diameter 2 to the 4th power minus 1? To the 4th power? Think about this. You could throw some numbers in. Let's just say diameter 1 was 4 centimeters. Diameter 2 is 1 centimeter. 4 diameter centimeters to 1 centimeter, right? That would be 4 to 1, 4 to the 4th power. What number is that? 64. That's a lot bigger than 1. What's the difference between 64 and 63? You could almost throw out that 1, -1. That's a nozzle. Guess what you can do to a nozzle? You can put it with a diffuser. A diffuser? If I took that diffuser and I went back out to the same exact area, the same diameter. Diameter at 1 is equal to diameter at 3. What are the assumptions of Bernoulli? Inviscid, no frictional loss. What do you think the pressure at 3 is going to be? Pressure at 1, you recovered it. What's the speed at 3 going to be? Back at 1. It's as if. So what happens is the nozzle is pretty easy to make and have a good efficiency, but the diffuser is a lot harder, because what in reality is when you try to have it opening up, the flow will sometimes want to slip around and get into little recirculation patterns right in there. So you have to be very gradual on the diffuser opening up. The nozzle you can neck down pretty fast, and it'll follow the flow. Okay. When you combine a nozzle with the diffuser is just trying to recuperate back up and not lose any of that mechanical energy of the fluid. What you have is a Venturi. A Venturi meter. So a Venturi meter, it just necks it down, goes back up, necks it down, goes back up. And what they'll do is they'll say, I want to measure the pressure over here and compare it to the pressure in the throat. I'll know the diameter 1 and the diameter 2 in the throat. And based on the pressure measurements, I can now tell you what the speed is at 1. And then if I know the area at 1 and the speed at 1, I can tell you the volumetric flow rate. It's a flow measuring device. It's a meter. It measures something. It's a Venturi meter. And we just did all the equations, but you can solve a problem like this. The inlet diameter is 6 centimeters. The throat is 3 centimeters. The pressure measured at the inlet is 210 kilopascal. and at the throat 160 kilopascal. Does that pressure look good, reasonable in the sense that it's lower in the throat? Sure, it's lower in the throat. Assume that air density is constant at 1.2 kilograms per cubic meter. Estimate the air flow rate. Estimate the volumetric flow rate or the mass flow rate of the air. You can do both, true? So going back, you just apply Bernoulli's equation along a streamline from 1 to 2, and you get that you can predict that the speed, let me just go back here. Let me just grab this equation. But what you have is you have that V1 is equal to P1 minus P2 times 2 divided by rho divided by D1 to the 4th over D2 minus 1 square root. Doesn't look pretty, but there it is. Does it make sense? So you could substitute numbers. 210 minus 160 kPa, kilopascal. Density 1.2 kilogram per meter cubed. The diameter centimeters are going to cancel, but you have 6 divided by 3 to the 4 minus 1. Now I have to be careful on my unit conversion. So a kilo is 1,000. A pascal is a newton per meter squared. A newton is a kilogram meter per second squared. True? I forgot to put in the square root. The kilo, pascal, newton, kilogram. I get a meter with this. That'll kick up a meter over here, so I'll get meter squared over second squared, take the square root, I got meters per second. But don't forget the 1,000. Don't forget the 1,000 on the unit conversion, okay? And so if we run this number, I think we get 74.5 meters per second. And then if we took and did the volumetric flow rate, I think it comes in right at 3.51 liters per second after some conversion. And then if you wanted the mass flow rate, multiply by the mass density, and I didn't do that, but you could get the mass flow rate. Let's spend some time on this problem, because this is a tough problem as well. We have a sealed water tank. At the top is air, and its air is pressurized at the top of the sealed water tank. But we have water filling 12 meters of the tank. So the height of the water in the tank is 12 meters. And the tank is connected to a hose. So here's the hose. It goes like this. And at the end of the hose is a little nozzle, just showing you a nozzle. And that nozzle shoots the water straight up. What we want to do is we want to predict the maximum height that the water could reach. What is H? It's not shown the scale, but you see what's happening there. All right? So how do you want to solve this problem? We're in the chapter on Bernoulli. Probably use Bernoulli's, true? So I know that's bad about textbooks. They say probably you shouldn't teach that way. But I don't know how else to introduce the concept and then apply it without having canned problems. But what we'll do is we'll introduce and go like this. And this is a case where this water jet is staying together and going up. It's against the gravity, and you get all the way up there to end the streamline. And in that streamline, yeah, you're going to assume still the lack of frictional effects and densities. You know, the air is not with breaking it all up, which is going to happen. So we're going to predict a maximum height that if you went out and tried to do this in the real air, wouldn't be achievable. So let me introduce some numbers for states. Let's say this is state 1. Right inside the tube, right down here is state 2. State 3 is right before the nozzle. State 4 is right after the nozzle. And state 5 is the maximum height. So those are our 5 points that I want to evaluate. So if I wanted to find H, how would I do it? Apply Bernoulli from 1 all the way to 5. So we have P1 plus 1/2 rho V1 squared plus rho G Z1 equal to P5 plus 1/2 rho V5 squared plus rho G Z5. That makes sense? Okay. How about the pressure at 1? Well, that's 150 kPa. So that's non-zero. How about the speed at 1? Large tank compared to small diameter outlet of the nozzle. Negligible? Okay. P5, pressure at 5. Atmospheric, we're going to work in gauge because this pressure is in gauge. And 1/2 rho V5 squared. 1/2 rho V5 squared. 0. And so what we find is that that Z5 minus Z1 is equal to P1 divided by rho G. What is this? Is this height? Is height? I'm sorry. Yeah, that's right. Isn't height? No. What is this height? I want to turn, this is not incorrect. H5 minus H1 is equal to this. But height is if I introduce a reference state right here, and I go up for Z, okay, then H is equal to Z5, and so, getting this all messed up, Z5 minus Z1, and so H is equal to Z1 plus P1 divided by rho G. It's equal to 12 meters plus 150 kilopascal divided by 1,000 kilograms per meter cubed times 9.81 meters per second squared. Worry a little bit about unit conversion, and so that maximum height that the water column can go is going to be 12 meters plus 15.3 meters. So the maximum height is 27.3 meters. See how we did that? All right. So if I increase this pressure, will it increase the maximum height? If the gauge pressure goes up. And you'll see that in the equation right here, P1. If I increase the height of this water tank right here, yeah, it's right there. It'll go up. True? Okay. Now I want to ask this question. What is the velocity exiting the nozzle? What's V4? How do you solve for V4? Bernoulli. You can do Bernoulli's backwards or forwards. You can go from 1 to 4 or 5 to 4 or 4 to 5. One way or the other. It really doesn't matter. Okay? So if we do Bernoulli from 4 to 5, what does the equation look like? P4 plus 1/2 rho V4 squared plus rho G Z4 is equal to P5 plus 1/2 rho V5 squared plus rho G Z5. Now, which term is 0? How about the pressure at 4? It's 0, 0. They're the same gauge pressure, 0. It's atmospheric pressure, so 0 gauge. We're looking for V4. How about Z4? Well, that's where we start our reference measurement. So that's 0. What is V5, that's at the peak. It's like throwing a ball up. The ball leaves your hand high speed. It goes up, 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 slowing, 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 and the gravitational field gets to the peak. It's got 0 speed at the peak. Then it falls down again. And then Z5 is H, isn't it? That's H. So we can find that V4 is equal to 2GH square root. Does that look okay? Is that okay? As a homework assignment, go from 1 to 4. The equations will look different. But then go back and use the equation for H you just calculated, and you'll get the same answer. It'll work. But it may be a little more tedious in the math. All right. What is the kinetic energy at 4? You can talk about the velocity pressure at 4, or you could talk about the kinetic head at 4, or you could talk about the head as energy per unit mass, like kilojoules per kilogram, or you could talk about head in meters, the velocity head in meters. We had 3 ways of writing it, okay? But so either calculate 1/2 rho V4 squared or 1/2 V4 squared or 1/2G V4 squared. Yeah, can't write V4 squared. One of those forms tells you what is the kinetic energy content of the fluid coming out. Either it's per unit volume, pressure, per unit mass, or per unit weight, head. Okay? So if you go ahead and calculate, let me roll down here a little bit, this kinetic energy at 4, you'll find that it's 267.7 kilopascals. That's this first one. It's also, I know I need to divide by rho, but it's also 267, so many kilojoules per kilogram, and hold it, I needed to divide. Let me try this again. I think I have a unit error here. If I take this pressure and I divide by rho, that's going to be 267.7 kilopascals times 1,000 kilograms per cubic meter. True? And a kilopascal times a meter cubed is a kilojoule. So this is equal to 0.2677 kilojoules per kilogram. Sorry, not 267. It's 0.2677. Now the last one, this is kinetic energy at 4 in different units. Kinetic energy at 4 is, if I take and divide by rho g, and then we get that the head is 27.29 meters, about 27 meters. That will be the head, the kinetic energy at 4. Okay? How far up did the water shoot? 27.3. It's the same. If you did the Bernoulli in the form of the head from 4 to 5, what would it look like? In terms of head, it would say the head come out in the form of kinetic is equal to the elevation head at 5. Okay, kind of almost going in a circle, but you could sometimes see the value of, speaking of the kinetic energy in energy per unit weight measured in meters. All right. All right. Let's ask this question. If the diameter on the exit of the nozzle was 1 centimeter and the diameter that fed it of the pipe or the tube was 4 centimeters, okay, you could go and calculate V3, the velocity at 3. See that? It's just our nozzle. We already analyzed the nozzle. We already know V4. What was V4? It's square root of 2GH. Did I give a numeric value for V4? It's 23.14 meters per second. So what about V3? It's a larger area. It's going to be a lot less, isn't it? How much less? Ratio to diameter squared. Okay, because of continuity, conservation of mass. It's so, go ahead and calculate this. You tell me what V3 is. I'm going to pause. You guys are sleeping on me. So we got that V3. Let me clean this up a little bit. V3 is equal to the area of 4 divided by the area of 3 times V4, true, from continuity. This is, the area is the diameter squared, so you had 1 over 4 squared times the 23.14 meters per second, and so we calculated that V3 was 44 meters per second. Now, what is the velocity pressure at 3? What do you mean velocity pressure? It's the velocity pressure at 3 is equal to 1/2 rho V3 squared. We just had calculated that V, square it, multiplied by 1,000, divide by 2. The speed at 3 is a lot slower. Well, okay, this is the exit at 4. This is the tube coming in at 3. Does that make sense? Okay. All right. So the velocity pressure, you just take 1.4, square it, multiply by 1,000, divide by 2, and what do you get for the velocity pressure? 7? 1037? 1.04 kPa. About a kPa, kilopascal. All right. So the velocity pressure, what's the velocity pressure at 2? The dynamic pressure at 2, the same as the dynamic pressure at 3. It's very, very small. It's very small, negligible almost, in the Bernoulli's equation. So what's now the pressure? I know I'm asking a lot of questions. I'm trying to move a little faster. But we said the pressure at 4 was 0 gauge. What about the pressure at 3, the pressure at 2? Is it going to be a high pressure at 3, a high pressure at 2? Are they the same? They're the same pressure. 2 and 3 have the same pressure. But what is the pressure at 2? What is the pressure at 3? How would you calculate it? Bernoulli's. That's exactly right. I'm running out of room. Sorry, I'm going to have to scoot down and just make do. So if you wanted to calculate the pressure, let's say at 3, it's going to equal the static pressure at 3 plus the velocity pressure at 3 is equal to the static pressure at 4 plus the velocity pressure at 4. The velocity pressure was 0 gauge. This is a whopping 1.04 kPa. The velocity pressure at 4, though, was quite high. All right? It's 267.7 kPa. All right? So the pressure at 3 is equal to 266.7 or thereabouts, okay? kPa, about 1 off. Make sense? If I put a pressure tap right in here, and I put a little pressure gauge right there, what will the pressure read? 266 or 67 kPa. If I put a pressure tap right here and I put a gauge on it, what will it read? Same. Okay. Now, what about, how can I also take a look at this? If I do a Bernoulli from 1 to 2, all right? If I do a Bernoulli's equation from 1 to 2, what does it show? Let me just write it out. Pressure at 1 plus 1/2 rho V1 squared plus rho G Z1 equal to pressure at 2 rho V2 squared plus rho G Z2, right? This is the velocity pressure at 2. We said it was about 1 kPa. This is 0 elevation. It's our benchmark. This meter, that was 12 meters tall, Z1. The pressure was 150 kPa gauge, and the velocity pressure at the top is 0. So the pressure at 2, just going from 1 to 2, is equal to 150 kPa plus the 12 meters, whatever hydrostatic head you get on that, rho G Z. When you do the 12 meters on the rho G Z, that pressure is, looking at my notes quickly, about 117. Okay? And then you take off the 1 kilopascal for the velocity pressure, and the pressure 150 plus 117 minus 1, what do you get? 266.7 kilo. It's consistent. It's consistent. Okay? All of that makes sense? As the fluid, talk about it like this. If the fluid packet starts here, has a lot of pressure and elevation, no speed. As it comes into here, it has some speed, right? The velocity pressure is about 1 kPa, a lot lower elevation, but a lot higher static pressure. So right before it comes into the nozzle, it's got its high static pressure and little velocity pressure and no elevation head or pressure. Then it goes through the nozzle, and that static pressure is really converted into kinetic pressure or velocity pressure. And then from 4 up to 5 is converted to gravitational pressure or head. Here's a question. We analyzed this system to death with that sealed tank and the gas or air above it at 150 kPa. I say remove a tank, the top of it. It's open tank. Same water level, 12 meters. But I put a pump. And the pump puts a differential pressure, a pressure gain of 150 kPa right there in the middle of that fluid line. Now, how high will the water shoot? And some students that have a hard time with this differential, just take, what did we say this pressure was right in here without the 150? It was about 117, 116, somewhere like that. Let's say it's 116 kPa right here, pressure gauge, and we have now a pressure gauge that reads, you add 150, it's 266 or 267 kPa, right? With the 1 kPa velocity pressure. So you're at 267 coming into that nozzle. How high will it go? It'll be the same. It'll be the same. Somebody says, I really, really, really would like to analyze a system like this where I have a pump in it using Bernoulli's equation. I got so good at Bernoulli's equation. No problem. We'll modify the original Bernoulli's equation to account for pumps putting energy in, turbines taking energy out, and if we can do that, we can modify it for some frictional losses. Some frictional losses. So there's modified Bernoulli's equation. So what did they do? First, get the pressure equation down before you go looking at too many equations. Between 1 and 2, they have something that has a pressure gain. What would that be? A pump. A pump. They could also have some loss. You could account for some frictional losses. Instead of putting the both on one side and have a negative in front of it, they put them on opposite sides and positives in front of them. But if you did have a turbine, it would be the pressure loss or energy per unit volume extracted by the turbine. I just said, okay, I'm going to be able to put a negative gain if I have to have a turbine. True. How did they move to the next modified Bernoulli's equation? What did they do? Divided the whole equation by, and we interpret each of the terms in there, even with this pressure gain and pressure loss because of friction on the loss and gain of a pump, we interpret them as energy per unit mass, some head, and there they are. I like to not use P anymore for the symbol for the gain, but to switch to something like cap H, head gain, cap H, head loss, knowing that that cap H is different than the third equation, lowercase h for head gain, where its units are implied by meter because it's head, and lowercase h loss. This is a great, you can do a lot of engineering calculations with the modified Bernoulli equation because you just follow the stream packet. Oh, it goes through a turbine, no problem. Goes through some viscous frictional losses through fittings, bends, unions, stuff like that. No problem, I'll account for it. Straight long pipe for frictional losses, I'll account for it. Right there. Okay? And then it goes through a pump. No problem, I'll account for it right there. So that's our modified Bernoulli's equation. This kinetic energy correction factor, what is it? Well, what we do is we took a look down the length of the pipe, okay, center line, and we look at the projection. And we say the fluid is moving a lot faster typically in the center than at the edges. So where does it move at constant speed? In little rings. That little ring of fluid has the same speed if it's symmetrical flow, and it is. Okay, and so that ring is at radius lowercase r. The thickness of the ring is dr. If we did the conservation of mass to get the equation for the average speed, we're doing that now. We're redoing it for kinetic energy. Hopefully this is almost the same song, but slightly different words. So if we're interested in the kinetic energy flow rate down the pipe, it's going to be the sum of the little kinetic energies that we're going to sum up, the little DEKs. Okay, and think about it for each ring. Each ring has the same speed, so the ring has the speed at that radius. We square it. All right, maybe I should put the square like this. Times 1/2 times the mass density. That will be the specific, well, hold it, do this, put over 2. Isn't that the specific kinetic energy? That's the kinetic energy per unit mass, multiplied by that mass flow rate, which is rho times the area times the velocity at that location. So now I can integrate that over the area, and that will give me the total kinetic energy flow rate. What we see is that velocity is a function of r, that velocity is a function of r, and so the kinetic energy flow rate is equal to the integral 1/2 rho velocity cubed dA. Wow, that looks pretty complicated. And we would like to use an equation where we say the kinetic energy flow rate is just going to be the 1/2 v squared, the average v squared, times rho v average area. That's what we like to do. So we can't do that. It's not going to give us the right equation, so we modify. We say introduce a fudge factor called the kinetic energy correction factor. Now we can use our favorite form, and alpha will be close to 1 often. But we see how you define alpha. Alpha is equal to the integral here, integral 1/2 rho v cubed dA, divided by 1/2 rho v average cubed area. And that's the same equation they give right here in the textbook. So cancel the half, cancel the rho, and we equal to the integral of the v divided by v average cubed dA divided by a. Same equation. This alpha, that alpha, kinetic energy correction factor, about 1 for turbulent flow, little over. Hydroelectric power plant receives water from a dam where the water level is 125 meters high behind the dam, and that feeds the turbine, which discharges the water at a level, another level. So here's our dam. Here's our input to the turbine, hydraulic turbine, and goes out. There's the base. Here's the water level feeding the dam. Here's the water level at the discharge. The height difference between the discharge and the water level feeding is h is equal to 125 meters. This turbine is hooked up to a generator who makes electricity, but the turbine slash, let me kind of draw it down here for generator, has an overall efficiency of 88%. You get some energy out of the fluid, put it into a shaft, from the shaft through the generator into electric power. So you go from fluid power, mechanical rotating shaft power, to electric power. The overall conversion, 88% efficiency. Determine the volumetric flow rate of water required to generate 100 kilowatts of electricity. So W dot electric is 100 kilowatts. That means that I need W dot fluid to be greater. What comes out of that water and the energy power out of that water flowing through the turbine, it needs to be greater by dividing by the efficiency of the turbine generator, which is 88%. And so if you have the 100% divide by 88%, you can find that you need 113.6 kilowatts, just intermediate calculation, of fluid power. Fluid power, okay? What you can do is you can go a Bernoulli from here all the way down through to right there. State 1 to state 2. Let's go ahead and write it. We can write it in terms of pressure, energy per unit volume. We can write it in terms of energy per unit mass, or head energy per unit weight, either one. So we have P1 plus 1/2 rho V1 squared plus rho G Z1 equal to P2 plus 1/2 rho V2 squared plus rho G Z2. What about these speeds? Their discharge speed at the lake at the bottom, negligible. the ingestion speed at the top, the beginning, negligible. Both atmospheric pressures. But one thing I forgot on this equation is that streamline had to go through the turbine, did it not? So you have the pressure extracted out of the turbine. You can put a negative pressure gain here, or you could put a pressure extracted by the turbine, energy per unit volume extracted by the turbine. Okay, we now can calculate the pressure, energy per unit volume extracted by the turbine in terms of pressure, which is going to be rho GH, because this Z2, you can just set it to 0, Z1 is H. So let's calculate this. It's 1,000 kilograms per meter cubed, 9.81 meters per second squared, height difference of 125 meters. We find that that pressure comes in, I don't even know if I made that intermediate calculation. It doesn't look like I did. If I take, this is interpreted as energy per unit volume. If I multiply energy per unit volume by volume per unit time, do I get power? Do I get power? Sure. And so the fluid power, W dot fluid, is equal to this pressure turb, fluid pressure turbine, times the volumetric flow rate, which is what I'm needing to calculate the AV. So the volumetric flow rate is equal to W dot fluid divided by P turbine equal to W dot fluid divided by rho GH. The volumetric flow rate, when you run the units, turns out to be 5.56 meters cubed per minute. Okay, if that came out of the fluid, but only 100 went into electricity, where did the 13.6 kilowatts of energy or power go? Frictional losses. And eventually, when you have friction, where does it just goes in increasing somewhere, some internal energy. And you say, well, did it heat up the water? And what you can do is if you assume that a 13.6 kilowatts of mechanical energy is dissipated into internal energy due friction in that turbine, and that is going to result in an increase in the temperature of the water, you can calculate the temperature increase of that water, assuming specific heat of 4.18 kilojoules per kilogram Kelvin, and you'll find that it's a whopping 0.035 degrees C. Are you going to be able to measure that? Not on a good day even. All right? So it's easily dissipated by making the water an itty bitty amount warmer. Thank you.